Section 6.1, the nature of light. Here's the objectives, things that you should really look for as we go through this. 1, name the model that replaced the Bohr model. Be familiar with what that is. Explain the idea of wave-particle duality, and be able to solve problems involving frequency and energy. Some of those things we've done already. So we're going to talk about quantum mechanics, which is the branch of physics where we're talking about those things at the really small level, the atomic level, the subatomic level. We get into those kind of things when we're talking about quantum mechanics. And if you really want to get into some of this stuff, you can see this equation over here, and you're welcome to work with that equation, do things if you want, but you know, I'm probably not going to get into that right now. All right, so we've talked about light in the last chapter, and let's talk about some different properties of waves, and we'll kind of relate that to light. First property that I want you to be familiar with is diffraction. So look at this screen up here, and this is what diffraction is. If you have a wave that's coming in, like these straight line waves coming in here, and they hit this barrier, but there's a small opening, what diffraction says is that the wave will spread out from that opening like it was just like a point. Like if you had just dropped a rock right there, you see the water wave go out from that. It would look like that. So, you know, when you have an opening like that and waves pass through it, they expand beyond that. That's known as diffraction. It's why you can hear people around a corner, because the sound waves diffract around the openings and through the openings so you can hear them. Okay, so that's one property of waves. Another property is called interference. When you have two waves, so down at the bottom we've got two waves that meet, and you know, kind of the bright spots, think of those as crests, and the dark spots, you know, are kind of the troughs where they kind of are in there. And if you have a crest and a trough meet, you know, so you get some areas where they meet and they kind of cancel each other out. So you can actually see where, like, you've got these lines where things have canceled out. So you've got these big areas, you know, the brighter areas, where, you know, waves, crests might meet and enhance each other and make them bigger, and areas where they cancel out. That's known as interference. So waves have those kind of properties. So think about water wave. If you get two big waves that meet, it gets to be one bigger wave. If you have a wave meet a crest or a wave meet a trough, it'll cancel itself out. So those are some typical properties of waves. Well, if light is a wave, then it should behave following some of those properties. And so they have done these experiments. This is a pretty common experiment called the double slit experiment. So they take a light source, and it goes, and we've got this opening here and an opening here, and as the light goes through that, we get interference patterns. So if you look at, if light were particles, what you would get is, I don't know if you can see that, you would get these particles going through there, and they would just hit the wall right there, and you'd get those bright spots right in front of where the openings were, and that's it. But because waves act and interfere with each other, you get these kind of patterns where you get these bright spots and then you get dark spots in between that. And that's what happens when you do it with light. If you do this with very small, it has to be very small openings, you will get these interference patterns. So this was what made them think that, hey, well, light must be a wave because you get these interference patterns. And that was kind of the idea for quite some time, that, you know, Maxwell's equations and says, hey, you know, it must be light must be a wave, and so, you know, we kind of just assumed that for quite a few years. Okay, so you get those bright talk about all that. All right, so along later comes this guy named Max Planck, and we've talked about him. That's Planck's constant, and he starts working with what's known as black body radiation. He's kind of, the idea is black body is kind of if you have a perfectly black object, it absorbs all light, doesn't emit any doesn't reflect any light, so it doesn't emit any energy like that. And then you heat it, you can kind of detect what's coming off of there. And in working with black body radiation, he found out that it acts more like particles. So you could put energy in, but you only got it out in discrete particles, in those quantum, those little packets of energy that come off. So he's talking about this black body radiation, and you get it in like these very discrete amounts, these quantum, these small units that come off of the box as it's reflected out. And usually if we're talking about light, we use the word photon. So quantum or photon, in terms of light, those two words are interchangeable. You wouldn't use photon if you're talking about something else, objects, metal, things. You just wouldn't talk about it with anything but light. And, so here's, once again, and we've done some of these equations, so these shouldn't be too bad, but these, here's an equation, and once again, it starts off Planck's equation, we got HF, where H is 6.6 times 10 to the negative 34, and, our energy is whatever we say. So if we say, hey, the energy of a photon is 3 times 10 to the negative 19th joules, what's my frequency? Well, remember, if I'm solving for frequency, I divide both sides by H, so frequency is going to be energy over H. It's kind of an E. Energy over H, and that's what they got there, and so you would get 2 times 10 to the 15th. Make sure that you're familiar with how to do that, or if we had, if we knew the frequency of a light wave, okay, I'm sorry, I guess it'd be 4.52 times 10 to the 14th. Now, if we have 2 times 10 to the 15th for the frequency of a photon, what's its energy? Well, you're going to multiply those two together and get 1.33 times 10 to the negative 18th. We've done these in the last chapter, doing them again here. Hopefully at this point these aren't too tough. So, all of this thing, kind of, they develop what we call the quantum theory, and really kind of the main idea to come out of there is that we're talking about energy in these discrete amounts, these quanta, these packets of energy. You kind of think of it like you've got a dish with marbles in it, and they're always, you can always add another marble or take a marble away, but there are always those little packets of energy amounts that are going in there. Nothing in between those marbles. Now, along with this, there's another property that kind of led scientists once again to believe, hey, it must be particles, and that's called the photoelectric effect. Einstein did a lot of stuff with this idea, and what this says is that if you have certain objects, if you shine light on them, they will emit electricity, and you can figure that. So it's a phenomenon in which electrons are emitted from the surface of material after the absorption of, that should be energy, okay, or light. So some kind of energy hits it, and it gives off electrons, which basically is electricity. So think of like a solar cell, solar panel. Light hits it, it emits electricity. That's kind of the photoelectric effect. And Einstein, like I said, did a lot of stuff with that, and used that to prove, used Planck's theory to prove the idea of the photoelectric effect and how that should work. Okay, looks like I need a little bit of work on my spelling there. Well, okay, so we say, hey, wait, light should be a wave, light should be particles, so really what is it? Well, it comes down to, now we have this idea that there's this duality. It actually is both. What light acts as a wave when it's traveling. It acts as a particle when it interacts with matter. So we kind of have this duality. So light kind of has properties of both waves and particles, and we kind of think it's both of those things. All right, there you have it.